So the recording has started. Okay, so let me start. Good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow, Department of Mathematics, IIT Patna. I am your NPTEL PMRF teaching assistant for the course Introduction to Probability Theory and Stochastic Processes. This course is offered by Professor S. Dharmaraja. He is a faculty in IIT Delhi. This is a 12-week course, and we are in the fifth week live session. So in the first 4 week, we have mainly discussed about the probability theory, okay, in which we discuss about the basics of probability, in which we discuss the definitions of probability, the classical and the empirical definitions of probability, and the axiomatic definition of probability. Then we have discussed random variables and their properties. Then the moment, moments and inequalities related to those moments, like Jensen inequalities, Markov inequalities, Chebyshev's inequalities. And in the last week, we discussed different kind of standard, discrete, and continuous distribution. This is the week 5th. And in this week, we will focus on higher dimensional distribution. In higher dimensional distributions, we have more than one random variable, and the distribution associated with those random variables are actually bivariate or multivariate density function, multivariate distribution function. With the help of those multivariate distributions or multivariate density functions, uh, we are able to calculate the marginal density function, and then we can calculate the different kinds of probability associated with those multivariate and marginal distributions, and the mean variance, etc. Okay, so we will start one by one. First, we will recap about some of the formulas used in this week, and then we will solve some numericals. So it's like before starting, let's discuss about what is random vector. Actually, when we discuss more than one random variables together, then those collection of random variables are called random vectors. So suppose we have x1 random variable, x2 random variable, x3 random variable, and so on, xn random variable. So like these random variables, this x is called a random vector which contain n random variables. Okay, so in higher dimensional dimensional distributions, we will use random vectors instead of random variables. Now, the first thing we will define is joint cumulative distribution function. So joint cumulative distribution function is like in univariate, we define, suppose x is a random variable which follows some distribution. Okay, so in that case, we define the CDF, the cumulative distribution function of this random variable x is like this, probability that x is less than or equal to x. In the same manner, in bivariate, we can define like this. Here we have two random variables, suppose x and y. So we can define like this, probability that x is less than or equal to x, y is less than or equal to small y. Small y's are the random values, random sample values, and capital R the random variables. Okay, so this is the uh, definition of the joint cumulative distribution function. Here, obviously, x and y can take any values, or we can define this in this manner as a it's like probability that omega defined in such that x omega is less than or equal to x and y omega is less than or equal to y for omega belongs to the sample space. If you can like recall, you will find that x, like here x and y are random variables. So these are actually a function which maps the sample values from the sample space to a real number with the help of this x and y function. Okay, so this is also the definition for the cumulative distribution function, joint cumulative distribution function. Uh, with the help of these joint cumulative distribution, before going there, we will first check whether a given two-dimensional random variable, two-dimensional function is a valid joint density function or not. For that, what we will do is to check if, suppose, let me write x1, x2 is a valid joint cumulative distribution function, then it satisfies hello then it satisfies some of the properties. As in univariate case, we define two or three properties. In the same manner, here also we define some properties. Like the first is here this fx1, x2 is non-decreasing, and continuous. From the right. Okay. So this two-dimensional function is actually a continuous function and non-decreasing in nature. With respect to each coordinate. Because it has two coordinates, that is two variable x and y. Also, as we know, if we take limit x1 tends to minus infinity and x2 tends to minus infinity, this value comes out to be 0 and limit x1 tends to plus infinity, x2 tends to plus infinity, comes out to be 1 because this CDF is actually bounded in within 0 to 1, including both. So these two property, and besides this, there is one more property actually. It's like, okay, let me draw a, suppose this is a like x-axis, this is y-axis. Okay, and we have some coordinates like this. Then in that case, suppose these are some of the values like this is A, this is B, this is C, and this is D. Suppose these are the some intercepts on x and y axis. Then for every AC and BD, these ordered pair, for every AC and BD with A is less than B and C is less than D, we have one more property that must be followed by this function. That is like f of BD minus f of BC minus f of AD and plus f of AC. This quantity, this quantity must be greater than or equal to 0. That is non-negative. Okay. If these three properties hold by a function, then that is the joint cumulative distribution function. Okay. So this is the definition. These are already discussed in the lectures V. Okay. If you people have any doubt, please let me know. Next is like how can we find the marginal now? Okay, these are the joint distribution. If I want some information related to the marginal distribution, okay, or some specific random variables, then we need to marginals. We need marginal CDF. Marginal cumulative distribution function. Also, in general, if we have joint distribution, then with the help of those joint distribution, we are able to calculate the marginal distributions like marginal CDF and marginal PDF. But if we have marginal CDF and marginal PDF, then we are not able to find the joint CDF or joint PDF unless and until we have some more information regarding those like distributions or random variables. Okay. Like if those are like independent, then we can multiply those two marginals to find the joint. But if we do not have any other information, then we are not able to construct the joint CDF or joint PDF via marginal CDF and marginal PDF respectively. Okay. So now we need to calculate or find the marginal CDF. So again, for the simplicity, let's take, we have random vectors. We have a random vector containing x1 and x2. Then if I want the cumulative distribution function of the random variable x, then it can be like defined as this, can be like defined like this. Okay, this is the basic definition. This can be calculated by implementing the limit on the other variable. Okay, so x2 tends to infinity, and then this. So this is how we calculate the marginal CDF of particular random variable. Similarly, if you want to calculate, like if you want to calculate the CDF for the another random variable, suppose x2 here. So this is like limit We apply the limit on x1 now. Probability that x is less than or equal to x1, x2 is less than or equal to x2. So this is how we calculate the CDF. Okay. Uh, in the same manner, suppose if we have nth dimensional random variable, then in that case, for example, suppose we have a random vector like this: x1, x2, xj minus 1, xj, j plus 1, and then xn. Suppose we have a random variable having n random a random vector having n random variables. Then in that case, if we need to find the marginal CDF of some particular random variable, suppose xj, so in that case, we apply the limit on x1, the limit on x2, and so on, the limit on xj minus 1, then the limit on xj plus 1. We omit xj because we need to find the distribution of the xj random variable. Okay, and then limit xn tends to infinity, and then this. Okay, so this is how we calculate the marginal fields, marginal is cumulative distribution function. In the same manner, we can calculate the PDF. This is the CDF actually. So in the same manner, we can calculate the PDF and PMF, the joint PDF and joint PMF. Okay. So joint probability mass function and joint probability density function. Okay. Suppose again we have a random vector having two random variables x1 and x2, and suppose it follows. Should write it. Okay. So in that scenario, suppose this is the CDF of the joint CDF and the random vector, then we can define the joint CDF in like the joint PDF, the joint PDF and joint PMF in terms of this. So in case of PMF, we can write like this: probability that x1. So let me first write like this, the notation: x1, x2, x1, x2. So which is probability that x1 equal to x1 and x2 equal to x2. This is the notation we use mainly in marginal, like discrete case. So this is how we can write. Or if you want, again, we can write like this: probability that omega such that x1 omega equal to x1, x2 omega equal to x2, when omega comes or belongs to the sample space capital O. Okay. So this is the definition of joint probability mass function. This is our joint probability mass function. Okay. So also it also has some property in the same manner. Like let me write it in remarks form. The first is, obviously, since it is a probability mass function, so it must contain within 0 to 1, including both. So that means probability that x1 equal to x1, x2 equal to x2 lie within 0 to 1. Also, if it is a valid probability, then its integral or its summation, depending on the nature of the variable, must equals 1. So that means if we take summation over the random variables x1 and x2, this probability function must give 1. Okay, so these two property must satisfy with this joint PMF, then it is a valid PMF. Okay, and now since we have a joint PMF, with the help of the joint PMF, we can calculate the marginal PMF. Please let me know if you people have any kind of doubt. Okay, now with the help of the joint PMF, we are able to construct or find the marginal PMF. How it is find? So suppose I need probability that x1. I need the probability mass function, the random variable x1. That is the x1 equal to x1, x2 equal to x2. This is the joint probability mass function, and we take summation. Since if we want the PMF of x1, then we take the summation with the support x2. Okay. In the same manner, if I need the PMF for the random variable x2, then we take the summation over x1 support. This is how we can calculate the marginal PMF with the help of the joint PMF. Okay. We can have one example here. It's like suppose E be a random experiment of testing an unbiased coin 3 times. Let E be a random experiment of tossing an unbiased coin. Tossing an unbiased coin 3 times. Okay. And we define, suppose, let me first write the sample space. As you people already know, if we toss 3 coins simultaneously or 1 coin 3 times, then we get like head, 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 tail, head, tail, head, and head, tail, tail. In the same manner, tail, head, head, tail, head, tail, 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 head, or tail, tail, and tail. These are the 8 outcomes when we toss the 3 coins. Okay. Now we define some random variables. Here the random variables are defined like number of heads. X is a random variable which is defined as number of heads. Okay. Y is also one another variable, difference in heads and tails. Difference in number of heads and number of tails, obviously. Okay. So here you can see the possible values of random variable X and Y are. So the possible X will be like what? Number of heads either 0 or 1 or 2 or 3. So that means possible value of X is either 0 or 1 or 2 or 3. Again, possible values of Y will be the difference. So here the difference is actually 3. Here the difference is 1. Here the difference is 1. Here the difference is 1. 1, 1. Here the difference is 3, not 0. Should I write 0? 3, 1, 1. So the possible values of Y is either 1 or 3 only. The possible values are either 1 or 3 only. Okay. So now we have total 4 possible values for the random variable x, and for the random variable y, we have 2 possible values. So obviously there is a total 8 combination possible. Okay. And with the help of those 8 combination, we have different sample values associated with those 8 combination. And then we can frame the joint probability mass function. Okay. For the random variable x and y. So let's start to construct the table first. Okay. So what are those table like? We have the random variable here. Here, like we have random variable x and y. So the possible values on x and y, and we have the sample. Okay. So see, x can take value 0, y can take 1. X can take 0, y can take 3. Similarly, x can take 1, y can take 1 also. No? And then x can take 1, y can take 3. Similarly, 2, 1, 2, 3, and at last 3, 1, 3, 3. So these are the possible 8 combination, okay, for the two random variables x and y. Now the sample. Here x is what? Just keep in mind, like x is the number of heads, and y is the difference. So if x is equal to 0, that means number of head is 0. So the number of head is 0 contains only if we get t. Okay. But in that case, y equal to 1 is not possible, because in that scenario, y equal to 3 also. So that means there is no sample values associated with this observation. So that means we can assign this as y. Simple. Again, if x is equal to 0 and y equal to 3, so this is the case now. Since x equal to 0, that means there is no head, and y equal to 3, that is the difference is also 3. So yes, this is the case. So that means this tail observation from the sample space is associated with this random variable 0, 3. Okay. In the same manner, x equal to 1, y equal to 1. So that means number of head is 1 and the difference is also 1. So obviously number of head is 1. So you can see here. Okay, let me erase actually something. Here it's t. So here what we are going to say, x equal to 1, y equal to 1. So the number of head is 1. So the number of head contains 1 is this, and this. And the difference is also 1. So that means all these three of samples belong to this observation. So that means what? So that means we can write HTT, okay, THT. It's THT, it's TTH. It contains the one head, and the difference between the number of head and the number of tail is 1. In the same manner, you can 1, 3, you can formulate 1, 3. So there is no sample values associated with this. So it contains 5. Again, 2, 1. So the number of head is 2. The number of head is 2. So this one, this one, and this one, and the difference is 1. So yes. So that means it contains like what? Head, tail, head, head, tail, head. Okay. And then it contains 5. Then it contains 5, and then it contains number of head is 3, and the difference is 3. So obviously head is the option. So that means head. So this is the probabilities, the formation of joint probability. Okay. So let's write it in numerical form, tabular form. So if you can see, you may find that here, right here. Suppose this is our random variable x, and this is our random variable y. Okay, why should I write like this? Okay, so this. So the y value contains either 1 or 3. The x can contain value 0, 1, 2, 3. Okay. So x is equal to 0, y equal to 1. X is equal to y equal to 1 have 5. So that means the probability associated with this is 0. X1, Y1 contains 3 elements. So that means out of 8, 3 elements are in favor of this 1, 1. So that means 3 by 8. In the same manner, 2, 1 also contains 3 by 8 and its 3, 1 contains 0. Now the rest 2 is like it's 1 by 8, 0, 0, 1 by 8. Okay. So this is how you can define the joint marginal density, joint probability mass function of the random variable when the random experiment is tossing 3 coins simultaneously and the random variables are defined as number of heads and the difference in heads and tails. And in that case, the joint probability mass function is defined like this. And from here, we can calculate the marginal probability mass function. So we can take run over y. So this is the y variable. So this is a marginal density function of y, which comes out by 3 by 8 plus 3 by 8 comes out to be 6 by 8, and it's 2 by 8. And for x, it is like 1 by 8, it's 3 by 8, it's 3 by 8, and in both the case, you can find that the summation comes out to be 1. So that means it is a valid probability mass function for the random experiments, which is defined just above with the random variables, number of heads and differences in number of heads and number of tails. Is it okay up to this point? Anyone have any doubt? Please let me know. So from here, you can calculate the expected value of x, the mean value of x, the mean value of y. We can calculate anything. Okay. The next is like joint PDF. In the same manner, joint PDF can be defined. Okay. Just replace the like what? Just replace the summation sign with the integral. Okay. So let me define the marginal PDF, marginal probability density function. That means we are now discussing the continuous random variable. Okay. So obviously, suppose we are given fx y. Suppose we are given a joint probability density function of the random variable xy. Then the PDF of x, the marginal PDF of the random variable x is we define it like we can take the support of y random variable and then just integrate this joint with respect to y, obviously. And when you need the y random variable, then in that case, we can take the integral over the support x. This is how you calculate the the marginal density function from the joint density function. It also have the same properties as we have discussed for the discrete case. So first will be like what? F x y. It is always non-negative. So that is either equal to 0 or greater than 0 for all x y belong to the sample space. And the second, there the summation over the two variables, here the integral. It's since I've written x and y. So it's fx y x, y, this comes out to be, sorry, dx, dy comes out to be 1. Also keep this in mind, or if we can take y in the integral and like y variable and the interior integral and x in the exterior, then we should write like this. Okay, so it's dy dx. Okay, so the ordering matters here. Okay, so this is the standard format to write these things. These are the property. Again, we have some more like questions related to these. So up to this point, if you have any doubt, let me know. If not, then we have one or two more topics to discuss and then we'll solve numericals. So the next is like independent random variable. Since we are discussing about the marginal random, sorry, the higher dimensional distributions, that means those distribution involving more than one random variables. So our one more aim is to check whether those random variables are independent in nature or not. So the next topic is independent random variable. So this is independent random variable. So for example, let's consider two random variables. So suppose x and y are two random variables. Okay. So these two random variables are independent if and only if. These two random variables are independent if and only if. There is if and only if condition. The xy, that is their joint cumulative distribution function, is like expressed as the product of their marginal cumulative distribution function for all x and y belongs to the answer. Okay, so in the ordered pair in the Cartesian plane, if this condition satisfy, if and only if condition, then we say that the random variable, like if this satisfy, then x and y are independent random variables. Okay, so this is the case. Also, if you have discrete case, then we can replace like this. So probability that x equal to xj, y equal x equal to xi, right? Y equal to yj is probability that x is equal to xi into probability that y equal to y. So you can see here now, if these are independent, then you are able to construct the joint density or distribution function from their marginal. But if there is no other condition, like here, if it is not independent, then you are not able to construct the joint with the help of the marginal only. Okay, so this is the case. The same case happen for the like continuous case as well. Like here, fx, y, xy is nothing but fx of x. Okay, so if x and y are independent, then this condition hold. Okay, if this is discrete, then this mass function condition holds. If continuous, then the density. So the next is like we have one more top, like we have one or two more theorem kind of things. Okay, since we are discussing about two random variables, now we are discussing about the functions of random variables. So if two random variables are like independent in nature, then is it possible their functional values, their functional, that is the transformed random variables, are also independent? So if there are some conditions, that yes, it is. So that is like actually if x and y are independent random variables and g and h be the some Borel measures function. That is g and h also function of random variables which is defined on the same probability space. In that case, the same condition has been satisfied. If the same condition has been satisfied, then we say that their gx and hx are also independent. Okay, so this is the case. Then there is one of the most important multivariate distribution is multivariate normal distribution or bivariate normal distribution. For simplicity, we will discuss bivariate normal distribution. Okay. So up to this point, if there is any question to anyone, please let me know. You can type bivariate normal distribution. So the bivariate normal distribution has some more properties as compared to the other bivariate distribution, like bivariate variable, bivariate uniform, bivariate exponential, any. This distribution has some specific properties as well. Okay, so that we are going to discuss here. So first thing is its notation. It's like if x, y, these are the two random variables, x and y. If x, y follows the bivariate normal distribution with the parameters. A normal distribution has two parameters. It has five. So it has two mu, that is mu1, mu2, sigma 1 is square, sigma 2 is square, and there is one coefficient is there, that is the association between these random variables x and y. So that is usually denoted by rho, which is called correlation coefficient. Okay. Here, obviously, you know mu1 and mu2 belongs to the real number. Sigma 1 is square and sigma 2 is square belongs to the positive, the non-negative real number. And rho is correlation coefficients, which must lie within -1 to +1, including both. Okay. So it has its closed form probability density function also. So it's like 1 upon it's 2 pi sigma 1 sigma 2 under root of 1 minus rho square. Now exponential of it's minus of 1 upon twice 1 minus sigma square. Then it has like the first one is like x minus mu1 upon sigma 1 whole square plus y minus mu2 upon sigma 2 whole square minus 2 times of rho of x minus mu1 upon sigma 1 y minus mu2 upon sigma 2 not sigma square. So this is the probability density function for the bivariate normal distribution. Okay. Now here you know that where x and y belongs to this, and it's like sigma 1 sigma 2 belongs to this. Okay, and this mu1 and mu2 is also there. Mu1 mu2 belongs to this, and this. Okay, then we say that this the whole thing that is written in this page only, that is visible to you, this is the probability density function for the random variable xy, that is the bivariate normal distribution. Okay, there are some properties associated with these bivariate normal distribution. Those are, if we are dealing with the bivariate normal distribution, then its marginal is also normal distribution. and its conditional is also normal distribution with well-defined parameters. Okay, so this is the property you may find in the normal case. When you are like dealing with the Weibull distribution, when you are dealing with some other bivariate or multivariate distribution, then you are not able to find these kind of like patterns or properties. Okay, so let me write. So first thing is like suppose this is xy is a bivariate normal random variables. Okay, so in that case, x follows normal with mean mu1 and sigma 1 square, and y also follows the normal distribution with mean mu2 and variance sigma 2 square. Okay, that is nothing just like univariate normal distribution with well-defined mean and variance. Okay, the second case is like if we are going to like estimate or calculate the conditional distribution. Suppose the conditional distribution of x random variable when y is conditioned. Okay, then in that case it also follows the normal distribution with parameter is like mu1 plus rho sigma 1, it's y minus mu2 upon sigma 2. This is the mean value for the conditional random variable x given y equal to small y. Here small y is some value actually. Okay. And the variance is like sigma 1 square, it's 1 minus 2 square. Okay. So this is the conditional distribution of the random variable x given y equal to y when xy follows the bivariate normal distribution. In the same manner, now you can write y given x is equal to x again follow the normal distribution. It's mu2 plus rho sigma 2. It's x minus mu2 upon sigma 1. It's x minus mu1. It's not x minus mu1 upon sigma 1. This is the mean and it's sigma 2 square 1 minus. Here you can also see if x and y are independent, then there is no correlation between them. And if there is no correlation, then in that case, sigma 1, 1 minus rho square terms vanishes. So that means, obviously, in case of independence, then x given y is equal to fx. Okay, there is no impact of condition in that. Okay, that is obviously you can take if rho equal to 0, then second becomes what? X given y equal to y becomes what? Normal of it's mu1 plus sigma times of the values. No? So that comes out to be 0. And sigma 1 square 1 minus 0 something is like sigma square, which is actually nothing but random variable x. No? Okay, so this is the case. Now, if you people still have any doubt, please let me know. If not, we will solve numericals. Anyone have any doubt? Okay, then we will solve some numericals now then. So the first question is the joint PDF of x and y is given by the joint probability density function of the random variables x and y is given by 2 e to the power minus x into the power minus 2y. Then x is greater than 0 and y is greater than 0 and 0 otherwise. So this is the given joint PDF of the random variable xy. Now calculate probability that x is greater than 1, y is less than 1. We need to find the joint probability that x is greater than 1, y is less than 1 when the PDF is given. Okay, so this is the simple question actually. You need only to solve the integrals actually. Okay, you need to just calculate the probability. Okay. So let's solve this. So we know that now, like we need to find the probability that x is greater than 1, y is less than 1. This is nothing but integral. Now let me first write the PDF e to the power minus x e to the power minus 2y. If I write here dx, then here the x limit will be there. So x will be like 0 to infinity, then dy, so it will be like y also from 0 to infinity. But here we need to find the probability that x is greater than 1, y is less than 1. So that means what? So that means we need to like define this. So how? X is greater than 1. So that means x can take value from 1 to infinity. And y is less than 1. So y is less than 1 means y is 0 to 1 because the minimum value of y is 0. Okay, sorry. That is y is greater than 0. So 0 to 1. So this is how what we need to calculate. So let's start calculating. So this is like what? First, we will solve the integral for x only. So y equal to 0 to 1. We can take 2 outside the x integral and e to the power minus 2y can also be taken outside from the integral over the x because it does not contain any x value. So it is like kind of independent from x. Okay, so now this is x from 1 to infinity. And here we can write only e to the power minus x dx and then dy. So our aim is to now calculate this first, then the other integral. So how we can write it? Like y from 0 to 1 to e to the power minus 2y. E to the power minus x, the integral of e to the power minus x is minus e to the power minus. It is minus e to the power minus x 1 to infinity. It's dy. Simple. Now we need to first solve this. So it's y from 0 to 1 to e to the power minus 2y. So it is like what? Minus e to the power minus infinity minus of minus e to the power minus 1. It's dy. Okay. So obviously you can solve this and you will find the first term comes out to be 0 and minus equals plus. So e to the power minus 1 will be the only thing that is remaining. So that is what? That is y from 0 to 1 to e to the power minus 2y. And after solving all these, we will get e to the power minus 1 dy. Okay. If there is any doubt, please let me know. Just simple calculation. Okay. Now the next step is what? Next step is to solve this. So we can take 2 e to the power minus 1 outside from the integral because it does not contain any variable. So integral y from 0 to 1 e to the power minus 2y dy. Now again, its integral is what? It's e to the power minus 2y divided by minus 2. Simple. So minus 2 or yes, y equal to 0 to 1 can also be written here. So it comes out to be minus e to the power minus 1. So e to the power minus 2 minus e to the power 0. Okay, so minus is there. So we can write this e to the power minus 1, e to the power minus 2, minus 1. Now minus e to the power 1 is multiplied. It comes out to be like 1 by e and minus 1 by e to the power. So this is our final answer. If since e has value 19 by 7, e has a value 19 by 7, like 2.7 something. So we can directly put those values. And once you will solve, you will find the e, this value is approximately 0.3679 minus its value 0.0498. So after solving, you will get probability that x is greater than 1, y is less than 1 is nothing but 0.318. So this is our final answer. Okay, just simple calculation. You can use your calculator or some other calculating device. Okay, so this is the probability. Any doubt in this question? Okay, then we will solve next question. Okay, so the next question is, so the next question is, let x and y be two independent binomial random variables. We are given like let x and y be two independent binomial random variables with parameters NP and MP respectively. Now, then the MGF of x plus y. Okay, we need to find the MGF of x plus y. Find the moment generating function, MGF, moment generating function of the random variable z, which is defined as x plus y. Okay, so this is the question. See, we are given the information related to the marginal distribution. Okay, so and we need to find the joint. So we are not able to like calculate the joint PDF, joint CDF, or joint MGF unless and until we have some more information. Here we have one more information, and that is like it is independent. These two random variables are independent. So with the help of that independent condition, we can proceed. Okay. So what we are given here is like we are given x follows binomial NP and y follows binomial MP. The like last week we actually discussed about the like properties of binomial variant. Okay, there you can see, maybe you can remember, if two random variables are independent and if those random variables have the same or identical probability of success, then we can directly write the like the distribution of those two, the summation of two random variables. Okay, but as we know, like we need to find the like MGF na, so we will use the prior information. So as we know what, if X follows this, Y follows in, then the MGF of X is what? The MGF of X is, it's like this. Okay, it's 1 minus P plus P e to the power T whole to the power N. This is the MGF when X follows a random, the binomial variate with N and P. In the same manner, in the same manner, it's 1 minus P plus P e to the power T whole to the power N, because it has the same probability of success but different number of trials. That is N. Since we are given one condition, since X and Y are independent, and as we know, when two random variables are independent, then its joint MGF is product of their marginal MGF. So that means what? That means 1 minus P plus P e to the power T whole to the power N multiplied by 1 minus P plus P e to the power T whole to the power N comes out to be like it's 1 minus P plus P e to the power T whole to the power N plus N. So its MGF will be like this. And since we know that uniqueness theorem of MGF, from the uniqueness theorem of MGF, we can conclude, although we need to find the MGF only, but with the help of this MGF, we can conclude this is nothing but binomial distribution again with the same probability of success P, but different number of trials, which is N plus N. Okay, so this is the case. Okay, so any doubt? This is just a property of the binomial distribution. Okay, then we will proceed for the next question. Am I audible now? Can anyone confirm?
Yes, sir.
You can at least. Okay, thank you. Okay, now the next question is like, suppose that a fair coin is flipped. A fair coin is flipped 3 consecutive times, and let X and Y be the random variables, and let X and Y be the random variables defined as like X will be defined as the number of heads obtained. Number of heads obtained, and Y is defined as the flip number where a head was first obtained. Flip number where a head was first. Okay. So the first time when the head was obtained, that flip number is the number of, sorry, is the y variable. Okay. Now we need to find. So that means what? If there is none, then we can define y equal to 0. No? Suppose we define there is no head at all, then that means tail, tail, tail. Then in that case, y equals up to be 0. Okay. Now the question is, see, the question is this, na? Is see, calculate probability. The probability that x is less than or equal to 2, y is equal to 1. We need to calculate this. Okay. So we flip the coin consecutively 3 times, and we define 2 random variables. X is the number of heads obtained, and y is the flip numbers where a head was first obtained. Okay. We need to calculate the probability that x is less than or equal to 2, y is equal to 1. Okay. So we will solve this again. Let me know if you are not able to understand the question. So here what? Here, obviously, the x is number of heads. So that means x can take values from 0, 1, 2, and 3. Simple. Y is what? Flip number at which, it's flip number at which first head obtained. So that means y can take any value. Na? It may possible that on the first flip we can get head. It may possible that on the second flip we can get head. It may possible on the third, and it may also possible at last there is no head at all. So that means 0, 1, 2, simple. And since we perform the flipping or tossing a coin experiment, and it is repeated 3 times, so that means the total number of possible outcomes is 2 to the power 3. So that means what? Total possible outcomes is what? It's 2 to the power 3 comes out to be 8. So total 8, again the same thing, just we have discussed. So let me write on the next page. So our sample space will be like this. The 3 head, the head tail, the head tail head, the head tail tail, tail head head, tail head tail, 2 tail, and then head, and at last we got 3 tail. Okay, so these are the 8 possible observations. Okay, now our aim is to find out, we need to what? Find out the probability that x is less than or equal to 2, y equal to 1. Okay, so see, we need to focus on y equal to 1 and x is less than or equal to 2. So first, let's focus on y equal to 1. So y equal to 1 implies flip number at which first head occurs. Okay. So y equal to 1 means flip number at which first head occurs. So at first, we will get the head only. Okay. So that is the case. And then x equal to less than or equal to 2. That means x is equal to 0, x is equal to 1, x is equal to 2. Okay. So if you are able to understand the problem, you will find that this favorable condition is we need either 2 head. See, first we need 1 head at least. Okay. So at least we need 1 head that is on the first flip. So that means we have only 4 possibilities. This one, this one, this one, and this one. Okay. So the maximum number of possible outcomes in our favor is actually these 4. And out of these, we have x is either equal to 2 or less than 2. So that means what? This one is not going to be the part of this favorable events. So that means what? The rest 3. So that means head, head, tail. It's like head, tail, head, and it's like head, tail, tail. So these are the only three possible outcomes. Let me write in a better manner. It's head, head, tail, head, tail, head, and head, tail, tail. So these are the only three possible outcomes which is in our favor for y equal to 1 and x is less than or equal to 2. Because for x is equal to 3, we have h, h, h. Okay. So we have three possible outcomes. Now it's simple. Na? Now probability that x is less than or equal to y equal to 1 is nothing, just 3 and total 8. So it's 3 by 8. Is it okay? Is there any doubt to anyone? Please let me know. Okay. So you can solve this. You can like able to calculate the joint probability using the probability density function. Sorry, probability mass function. Uh, okay, let me know. We will go for the next question now. The next question is the similar kind of, but the conditional. Let n x and y be random variables which with joint probability density function is given by. So we are given let x and y be a random vector with two variables, obviously, with joint probability density function is given by it's like 24x square upon y cube. When x can take value this and y is greater than 2. Okay. And 0 otherwise. We need to compute probability that x is less than half given y is greater than 6. Okay. Give me a second. Am I audible? Okay.
Yes, sir.
The question is this. Okay. The question is this. No? We have two random variables with the joint PDF is given there. We need to find the conditional probability now. Okay. So let's start. So what we can do is like, as we know, na, probability that A given B is what? Probability that A intersects and B divided by probability B. So A intersection B is that is associated with the joint. Okay, that is associated with the joint medium. Okay, and then the denominator is marginal. So let's start. So that means what? That means probability that x is less than half given y is greater than 6 can be written as probability that x is less than half y is greater than 6 divided by probability that y is greater than 6. See, for the numerator, we will use the joint medium. Okay, and for the denominator, since probability that y is greater than 6, it only includes y but not x. So that means we need to find the marginal distribution, marginal density function of the random variable y to calculate that. Okay. So first start with the numerator part. So now it's probability that x is less than half, y is greater than 6 is, we can write our density function, which is what? 24x square upon y. 24x square upon y cube. We can write either x or y. Okay. So it's if dy by d, if dy into dx you can write, or you can write dx into dy. Since first I have written dx, then dy. So first is then the limit for the x random variable, and x can take value less than half. So that means what? From 0 to half. Simple. Okay. Now y is greater than 6, and the value of y is greater than 2. No? Here. So greater than 6 implies what? Y equal to 6 to infinity. So let's start again in the same manner. Our first aim is to like what? Y equal to 6 to infinity. We can take 24 upon y cube common because it does not contain any x. Now x from 0 to half, x square dx, and then dy. So we can write like this: y equal to 6 to infinity, 24 upon y cube. Now x square, the integral of x square is what? X cube upon, simple. And the range is like the limit is this to this, dy, simple. So the next step is to what? Y from 6 to infinity. It's 24 upon y cube. So it's x cube by 3. So we can take 1 by 3 common. So it is like 1 by 2 to the power cube. So 1 by 2 cube implies 1 by 8 minus 0 dy. So if you can see, you will definitely find out that we can simplify this as 1 upon y cube dy. Okay, because 1 by 3 into 1 by 8 comes out to be 1 by 24, and in numerator we have 24. So it will cancel out and gives 1. So this is our now case. Now again, y cube can be written as y to the power minus 3, and then it can be written as like something like that. It's minus of 1 by 2 and y square. We can write like this, and its integral will be from 6 to infinity. Now you can put the value of infinity at y, then you will find out 0. So it's minus 1 by like kind of infinity comes out to be 0, and then minus comes out to be plus 1 upon 2 into 6 square. So this value, the probability value at x is less than half, y is greater than 6. X is less than half, y is greater than 6, comes out to be 1 upon 6 square is 36, 36 into 2, 72. So 1 upon 70. So let's call it equations. Okay. So the numerator part comes out to be 1 by 72. Now it's the denominator term, that is obviously the probability that y is greater than. Okay. Okay. For that, now probability that y is greater than 6. For this, we need the marginal distribution of y. So first, we will calculate fy, which is integral over x, fxy, xy dy. This is the formula. Okay. We can put the values like the integral of x is what? the range of x is 0 to 1 and 24x square upon y cube. Okay. So x is like 0 to 1, it's 24 x square upon y cube dy. Since it is a function of y, na, so we can take x common. It's 24 x square is taken outside. Okay, I have made some mistake actually here. We need to find the marginal of y. Na? So marginal of y, that is x. So that means here I need to write x. Na? X, x. So it is a function of x. So that means 24 upon y cube is taken outside. And then x square is within the integral. So obviously it's x cube by 3. It's 0 to 1. Now it's what? 24 upon y cube. It's 1 by 3 minus 0. So it comes out to be, it's 8 upon y cube. When the value of y, the range of y is what? The range of y is something greater than 2. No? Yes, it's greater than 2. When y is greater than 2. So this is our like this is our marginal PDF of the random variable y. Okay. Now the next step is to find the probability. Now the probability that y is greater than 6. We need to calculate the probability if y is greater than 6. So probability is y is greater than 6 is what? Y from 6 to infinity. It's 8 upon y cube dy. So 8 is taken as common. Okay. Yes, this is okay. And 1 by y again, 1 by 2y. Is there, it's 6 to infinity. Now you need to solve this. Okay. That's simple. You need to solve this. And it can be solved via like 8 is there. When you take the value infinity, it comes out to be 0. I'm putting directly 0. Here it's plus. It's okay. I have made one mistake. No, it's not y, it's y square actually. Okay. So the next is 1 upon 2 into 6 square comes out to be 1 by 72. So probability that y is greater than 6 is nothing but 8 by 72 comes out to be 1 by. Okay. Now the final part is x is like less than half given y is greater than 6 comes out to be probability that x is less than half y is greater than 6 divided by probability that y is greater than 6. Putting the values, the numerator values 1 upon 72, the denominator values 1 upon 9. It's 1 upon 72 into 9 upon 1. So probability that x is like less than half given y is greater than 6 is nothing but 1 by 8. So this is our final probability. Any doubt? Anyone? Okay, so we will move for the next question. Okay, then now the next question is now we will calculate the mean variance kind of moments. Okay, so we are given the joint PDF of xy is given as if the joint probability density function of the random variable xy is given by, we are given the question like this. It's 2 when x can take value from 0 to 1, including both, and y can take value from x to 1. Okay, and 0 otherwise. Simple. Now, what we need to do is we need to calculate the expectation of x square. Okay, simple question. We need to find the x square, expectation of x square. Now, see, as we know, the expectation of x square is what? Since it is a continuous in nature, so it is like x square into x dx, simple. And we are given the joint distribution of random variable x, y. So our first aim is to find the marginal of x. So that means what? Marginal of x. So marginal of x is integral over y, xy, dy. This is the formula. So y's integral is what? Y, the range of y is from x to 1. So we can take x to 1, and then fxy comes out to be 2 dy. 2 is taken as common. Dy, the integral of dy is y, and the limit is x to 1. Simple. We can take value, so it's y minus x. It's x. And the value of x is like 0 to 1. So this is our marginal probability density function of the random variable x. Now we can calculate any value. Now. So we need to calculate what? Now we need to calculate expectation of x. Okay. Now we need to calculate expectation of x. So that is nothing, but x has 0 to 1 integral. So it's x square into 2, 1 minus x dx, which is what? 2 we can take outside, integral 0 to 1. It's x square minus x cube. If you like distribute x square into 1 minus x, then it comes out to be like this. It's 2 is there. So x square, the integral of x square is x cube by 3 minus x cube is x to the power 4 by 4. The integral from 0 to 1. So it's 2 is there. So it's 1 by 3 minus 1 by 4 minus 0. So it's simple. No? 2 into it's 12. It's 4 minus 1 comes out to be 1 by 6. By 6. Suppose if we can calculate some more observations, let's calculate the variance. Okay. Now, variance of x. Variance of x is what? Variance of x is something like x, expectation of x square minus expectation of x whole square. We have already calculated expectation of x square. Now, let's calculate expectation of x. So expectation of x will be like what? 0 to 1, because the range of x is 0 to 1. It's twice of, we have twice of 1 minus x. Twice of 1 minus x, and x is multiplied dx. So again, 2 is there. We can write 0 to 1. It's x minus x square dx. So its expectation of x is what? Twice is there. It's x square by 2 minus x cube by 3. And it's 0 to 1. Its 2 is there. So it's like 1 by 2 minus 1 by 3 minus 0. So 2 multiplied by 6. It's 3 minus 1. So it's to 1 by 3. Okay. 1 by 3, that comes out to be 2 by 3 actually. So expectation of x is 2 by 3. Now, Variance of x. Variance of x is what? Expectation of x square, which is 1 by 6, minus expectation of x whole square, which is 2 by 3 whole square, which is 1 by 6 minus 4 by 9. We calculated something wrong. It may possible because this is not the question. I have like, so it's like what? 9, 18 is there. Expectation of x square minus expectation of x whole square. Okay. Have we calculated right now? It's 3 minus 2, na? Yes. It comes out to be 1 by 3, not 2 by 3. That's why I'm confused. It's all because the variance always comes out to be positive, no? So max to max 0, minimum to 0. See, okay. So we can write here like this, 1 by. So it's like 3 minus 2. So variance of x comes out to be 1 upon 18. Simple. Is it okay up to this point? Okay, then we will solve next question. The next question is like something interesting. The next question is like, let x and y be independent random variables. Let x and y be independent random variables taking values in the positive integer. Taking values in the positive integers and having the same PMF and having the same probability mass function fx, or we can write px if you want. Okay, it's 2 to the power minus x. Then x can take any value from 1, 2, 3, and so on. Okay, this is the question. Now, the main question asked is find probability that minimum of xy is less than or equal to x. Okay, our question is this: x and y be the independent random variables, taking the values in the positive integer. That means it is discrete kind of nature. And the PMF is defined as 2 to the power minus x, for x can take any value 1, 2, 3, and so on. Now we need to find the probability that the minimum of x and y is less than or equal to x is what? Okay, so let's solve this question. Okay, so what we are given here, we need to find probability that minimum of x, y is less than or equal to x. Okay, so here just can think like minimum of x and y is less than or equal to x. It may possible x is less than or equal to x and y is less than or equal to x as well. So we can like use the complement of probability property. Okay, the property of complement. Okay, and we can like draw some more information from the same probability that minimum of x, y is less than or equal to x. Okay, we can use the complement property and we have more information than this. How, what can we can write? We can write like this. No? Probability that minimum of xy less than or equal to x. This can be written like this. No? 1 minus probability that minimum of xy is greater than x. You can write like this, simple. Less than or equal to x, then it's 1 minus greater than x. Simple. This is the complementary property of probability. Now you can think. Now you can think, since minimum of xy is greater than x, so it simply means the another variable is also more than x. Okay. So it's have more information as compared to the previous wording. Okay. Or we can write like this: 1 minus probability that minimum of xy is greater than x. This implies x is greater than x, y is greater than x. Okay. Because the minimum is greater than x, implies the other one is also greater than x. I hope it can be like, give me a second. Okay, so this is the case. Now, since x and y are independent, it is given in the question. It is given in the question that x and y are independent. So that means what? So that means we can write this, na? X is greater than x, y is greater than y as probability that x is greater than x into probability that y is greater than y. Because this is the necessary and sufficient condition for two random variable to be independent. Okay. And there is also one case. It is also given have this like same PMF. It is also given. It has the same PMF. So that is 2 to the power minus x. We can write directly. So that means what? We are given probability. It's like x is equal to 2 to the power minus x. In the same probability that y equal to y also have 2 to the power minus x because have the same PMF. Now, our question is what? We need to find probability that x is greater than x. So let's write probability that x is greater than x is what? Probability that x is equal to x plus 1. Greater than that means x is equal to x plus 1 because it is a discrete in nature. Plus probability that x is x plus 2 and so on. Or we can write like this because this is given 2 to the power minus x. So that means it's 2 to the power minus of x plus 1 plus 2 to the power minus of x plus 2 plus 2 to the power minus of x plus 3 and so on. Simple. Now you can simply understand this is infinite geometric series actually. Okay. So since it is infinite geometric series and we know that suppose it's a plus r, not it's plus, that is in EP. Na? Here it's GP. So AR plus AR is square plus so on. So it can be written as like A upon 1 minus R if modulus value of R is less than 1. Okay. If modulus value of R is greater than 1, then it is R minus 1. Yes. So here A equal to, you can compare, A is the first term. So here A equal to what? 2 to the power minus of x plus 1. And R is obviously 1 by 2. Okay. So probability that x is greater than x is actually 2 to the power minus of x plus 1 divided by 1 by 2. It 1 by 2 goes in numerator multiplied. So it is simplified as 2 to the power minus x. Okay. Now, since it is a, so that means what? Probability that y is greater than x can also be equal to 2 to the power minus x. Now, we need to find what? We need to find this, na? X is greater than x, y is greater than x. y. Okay, I have written y greater than y, but it should written y is greater than x here. Okay. Okay. So that means what? Probability that x is greater than x, probability that y is greater than x is nothing but 2 to the power minus x into 2 to the power minus x. That means a square comes out to be like what? 2 to the power minus 2x, which is actually क्या? What 4 to the power minus x. Na? 2 to the power 2 to the power minus x, that is 4 to the power minus x simply. Now, our actual aim is to like find the probability that its minimum of xy is less than or equal to x, which is equal to 1 minus probability that x is greater than x, probability of y is greater than x. So our final answer will be like 1 minus 4 to the power minus. This is our final answer. Any doubt in this question? Anyone? Okay, then. If not, then we will solve the next question. Okay, maybe it's the last question. So the question is like, let x and y be two independent Poisson random variables. Let x and y be two independent Poisson random variable with parameter lambda1 and lambda2 respectively. Okay. Now we need to find the distribution of x plus y. Find the distribution of random variable z, which is defined as x plus y. Okay, so this is the question. So how can we solve? We are given some information. Okay, it's similar like the binomial question that we have just solved. So it's like we are given x follows Poisson lambda1, y follows Poisson lambda2. So that means what? Probability that x is equal to x is e to the power minus lambda1, lambda1 to the power x on x factorial, or x is equal to 0, 1, 2, and so on, and lambda1 is greater than 0. Okay, this is the marginal. Now again, the probability that y equal to y is what? E to the power minus lambda2, lambda to the power of y upon y factorial. So it's will be like y equal to 0, 1, 2, and so on, and lambda2 is also greater than 0. These are given. Now, we have also given one more thing, independent. Okay, since these x and y are independent, then we can multiply directly. But once you multiply this, you will not get anything because here lambda1 and lambda2 are two different parameters. Okay. And lambda 1 to the power x and lambda to the power x is also two different. Okay. So what I'm suggesting is we can directly use its MGF. Okay. We can directly use this MGF. So what is the MGF of the first parameter? E to the power lambda 1 and e to the power t minus 1. This is the moment generating function for the Poisson variate with parameter lambda. And similarly, we can write this has already been like discussed in the previous lecture. Okay. If anyone have any doubt, then we will obviously can discuss this class as well. But we can directly use this formula because we already know the MGF of the Poisson variate. This is the form. And since x and y are like independent random variable, so that means what? So that means m x plus y t can be written as mx t into my t. Simple. So from here, e to the power minus lambda 1 to the, sorry, this is the PDF, no? Why should I write this? So it's like e to the power lambda 1, and then it's e to the power t minus 1 multiplied by e to the power lambda 2, it's e to the power t minus 1. Now, since both have the e to the power has the same thing kind of, so if e to the power t minus 1, and then it's lambda 1 plus lambda 2. Okay. And if you compare, you will find nothing but like this z parameter, sorry, z random variable, which is x plus y, actually follows Poisson distribution with parameter lambda 1 plus lambda 2. Is it okay? Any question? Okay. I have one more question actually. We can solve this question as well. Okay, this question is actually based on independent random variables. Okay, we have questions. So we are given like let x and y be independent random variables. Let x and y be independent random variables, each taking a values each taking the values -1 or +1 with probability 1/2. Okay. And let we define another random variable which is z, which is defined as the product of the random variable x and y. Then which of the following statement is or are true? Then which of the following statements is or are true? So the statements are like this. The first one is x, y, and z are pairwise independent. Okay. So B and X, Y, and Z are pairwise not independent. The third option is X, Y, and Z are independent. And D is X, Y, and Z are not independent. So we have already discussed the meaning of independent and pairwise independent. Okay. For pairwise independent, all possible pair must follow the rule of independence. Okay. And when we are talking about independent, then all available variables must follow the property of independent or definition of independent. Okay. So this is the case. So let's solve this question. Okay. So what we are given here is actually, just give me a second. Yes. What we are given here is X and Y can take only two possible values, -1 and +1, and having the probability 1/2, 1/2, and Z equal to X into Y, the new transform random variable. So what we are given is like here X and Y can take any value, but from -1 and +1 only. Okay. And with the help of this -1 and +1, we have Z values. Okay. So let me write, suppose it's X, it's Y, it's Z. So X has -1, -1, +1, +1, because X has two possible values, Y has two possible values. So there is a total 2 into 2 equals 4 combination. So it's -1, +1, -1, plus. So yes, Z is nothing, just a multiplication. So -1 into -1 comes out to be +1. Minus into +1 comes out to be -1. Plus into minus comes out to be -1. And 2 plus comes out to be plus. Okay. So this is the value of Z. Now, here we can directly see, since the probability of each row comes out to be 1/4 directly, we can see. So that means probability that any value like X is equal to -1, Y equal to -1 comes out to be 1/2, sorry, 1/4 and all, because there are only 4 possible combinations. Now the question is to check the independence and pairwise independence. Our question is to check the independence and pairwise independence. Okay. So let's start with first. So first let's take X and Y. Okay. So let's check the independence of the random variable X and Y. So you can take any value. Okay. So what I am going to take is probability that X is equal to 1 into probability that Y equal to 1. You can take -1, +1, any value. So what is it? It is already given here. If you can see, the probability is half. So the first probability that X is equal to 1 is half into probability that Y equal to is half equal to 1/4. And 1/4 is what? Here you can see this, which is what? Which is probability that X is equal to 1, Y equal to 1. So that means what? That is X and Y are like independent. Here X and Y are independent. Okay. And yes, you can take any value. Actually, this condition must hold for all values. I'm just showing here one values. You can check -1 + 1 is also comes out to be the same. So this is the case. This is how you may solve. Okay. Now the next is we have taken x, y. Na? So now we can take x and z. X and z random variable. Okay. So you can also see z has also the similar kind of structure. Okay. So here, since okay, since z equal to define z, na? Z equal to x into y. Okay. So let's check. Let's check probability that x is equal to 1, z equal to 1. Okay. So from the table, x is equal to 1, z equal to 1. X equal to 1, z equal to 1. We have only this condition. For x is equal to 1, z equal to 1, we have only one condition, that is y equal to 1. Okay. So that means what? You can see here. For x is equal to 1, z equal to 1, we get y equal to 1. There is only one condition, y equal to 1. It is necessarily we will get y equal to 1. There is no other option. So that means what? So probability that x is equal to 1, z equal to 1 is 1 by 4. It is already calculated from here. All have the same probability 1 by 4, 1 by 4, 1 by 4, and 1 by 4. The next is to like we need to find probability that x is equal to 1, which is 1 by 2. Now we need to find the probability that z equal to 1. Okay. And z equal to 1 have only one probability for x equal to 1, y equal to 1, which is this, and z equal to 1 with this. So that means it's 1 by 4 plus 1 by 4 comes out to be probability that z equal to 1 have the probability 1 by 2. Here from here you can see directly. Z has two probability. Now for x equal to 1, z equal to 1, we have some other kind of probability. Like probability that x is equal to 1, z equal to 1, equal to 1 by 4. Probability of x is equal to 1 into probability of z equal to 1 equal to 1 by 2 into 1 by 2 equal to 1 by 4. So this implies what? This implies x and z are independent as well. Simple. In the same manner, you can replace x with y. Please let me know if there is any confusion. In the same manner, sorry, we can replace like y and z. Again, we can take y equal to 1 and z equal to 1. Okay. So probability that it's y equal to 1, z equal to 1, which comes out to be 1 by 4. Now, probability that y equal to 1 is 1 by 2. Probability that z equal to 1 is 1 by 2. So obviously, you can find out that probability that y equal to 1 into probability that z equal to 1 equal to 1 by 4, which is probability that y equal to 1 equal to 1. So that means what? Y and z are dependent. So that means what? So that means we can like conclude something like this. Na? X and y independent, y and z independent, and x and z independent. This implies x, y, and z are pairwise independent. Is it okay? Because there are three variables and there are three possible combinations. xy, yz, and xz. And all these three combinations are follow the independent rule. So that means these are pairwise independent. Simple. Now the next step is to find whether these are mutually independent or not. That means all the three are independent or not. So that means what? Okay. Probability that x is equal to 1, probability that y equal to 1, probability that z equal to 1. Obviously, it has probability 1 by 2. It also has probability 1 by 2. It also has probability 1 by 2, which comes out to be 1 by a. Okay. Now, we need to find the probability that x is equal to 1, y equal to 1, z equal to 1. Again, let's go to the table. X equal to 1, y equal to 1, z equal to 1. Okay. So actually you can see, obviously it's nothing but 1 by 4 directly we can see here. Or you can see that since x and z are associated with y, okay. So if x is equal to 1, z equal to 1, then y must be equal to 1. Okay. So from there also, you can directly calculate this value and comes out to be 1 by 4. So what? So probability that x equal to 1, y equal to 1, z equal to 1 is not equal to probability that x is equal to 1 into probability that y equal to 1 into probability that z equal to. So that means what? X, y, and z are not independent. Is it okay? That means x, y, and z are pairwise independent, but these are not mutually independent or in general independent. Okay. So this is the case. Any other question, anyone? Okay. If you people have no questions, so I think we can conclude our session here. If anyone have any doubt, please let me know. Anyone? Okay. If you people do not, okay, thank you. So if you people do not have any question, then we can conclude our session here. So thank you very much, everyone. Let me first stop the recording.